am from Bohemia Interactive Simulations, where I am working as a designer. And for this evening, I have prepared a presentation about sensors. And sensors that is architecture for describing environment for agents, for artificial intelligence. Before we start, I would like to point you that there exists online version of those slides on this online address. So anyone of you who's interested in checking that on your touch screen device, or anyone who wants to ask me some direct question which can be answered after the presentation, you can use the online version of the slides. Just go on this page and write your comments. So let's start with some very brief outline of the presentation. So we start with motivation sources. So why we do this kind of AI, this is why I talk about sensors, and where the system or the architecture I described is already used. So we'll be talking about some examples, about some business, etc. In the second part, we get to the one sensor definition. Again, we try to do that on practical examples, so you will hear some close to reality example of customer which is requesting some AI feature, and we try to use sensors approach to satisfy him. And based on that, we try to do some one sensor definition, and we try to somehow figure out where fits the sensor architecture to the rest of the simulation system. And at the end, there is coming I hope the interesting part, because everything up to here, it looks very primitive. I think anyone of you will be thinking that it's very simple, and even for non-AI developers, I think it won't be anything complicated. Here it starts to be complicated, and here I would like to show some benefits of the system. So I will show some complex example, we will see some video of the AI using the sensors, and we get to the benefits, limitations, and we discuss what's good and what's bad, etc., etc. One step back. So I said that I'm from Bohemia Interactive Simulations, which is a company developing military simulations for military groups, customers, usually armies, so all the good armies in the world, so no China, you know. And our flagship product is virtual battle space, in short VBS, version 3, which is huge sandbox military simulation. We have thousands of types of units there, so we can imagine Arma 2 or 3, something like that, with a lot of realistic tanks, soldiers, airplanes, ships, and a bunch of special technologies like UAVs, bombs, different types of terrorists, even pregnant ladies with bombs, etc. Soldiers, and not just soldiers, also other people are training real-life procedures, cooperation, so they are not trying how to shoot from a weapon, from personal weapon, they are more trying how to coordinate themselves if 4 people are sitting in a tank. They connect, they are not just using VBS3, they are using their own systems like flight simulator of F-16, and they connect, for example, 5, 7, 10 types of simulations together, and there are, for example, thousands of people training at the same time, or maybe hundreds is usual, thousands is not as usual, but hundreds of soldiers sitting at computers and trying to do something that's usual. There are tens of thousands of soldiers trained on this every year. So. And how it is related to this presentation. I am a designer in Team C, which is control team creating VBS Control toolkit, which is framework which serves for developing AI. And to stop talk about boring business stuff, I will show you some video from the latest release of the VBS, so you can see what kind of features soldiers request and what they get. And I said that I'm here as a representative of Bohemia Interactive Simulations, but also I'm representing here notAlab, which is a group of developers binded around the Spring RDS engine. It's a free project, it's my hobby, and also there is growing RDS game called Nota. It's slightly different from what you can see in VBS. There are high fidelity detailed soldiers. There you can see a bunch of thousands of robots, 150 types. We are using AI for different purposes, as micro AI, as opponent AI. We are also faking that there are players playing our game, so there are some bots in battle rooms waiting for players, and they behave like they are real players. And we are populating our servers with those fake guys. And I think you deserve another video, so you have at least basic feeling what is this game about, and our projects what are about. So this is not a game. And there is an alert. As I said, we are big money makers. So even on this, we just earn $1. You see that we like explosions. That we sometimes use some auto annihilation models. And yeah, and there should be another nuke explosion, yes. Okay, so this is nota. It's free to play, and you can search for that on Google and join us. So, those were the two groups of people which are using for some purpose our sensors. So now we get to the why and how we construct sensors. So you still don't know what the sensors are, but I can start to talk why we do that and what are the sources. So our commercial business cases. There is customer coming to us. He wants to simulate military behavior. Squad of soldiers somewhere in the forest fighting with anything they meet, and they give us field manual for such squad guys just with personal weapons, and it is usually 500 pages of rules. So if you want to be a good soldier of any NATO army, you need to know all the information on those 500 pages, and you can imagine that making AI which is following all the rules, it's almost impossible. It's entirely impossible. Other example is that we are creating RTS nota game where we are just 2-3 guys. We cannot afford dedicated AI developers unless we enslave someone. And so we have no money, we have no resources to afford to generally pay someone who will create AI for us. I can do that in my spare time during the lunch pause, but it's not much time. So those are two motivation sources, and you will see that the results coming from those kind of different use cases are the same. So what we try to minimize the necessary experience level of the people which are making behaviors for us. We want to make tools or sense of architecture which is so user-friendly that even people without AI education or AI practice are able to join us, help us, and do something useful which we can use in our products. It may be applied in the company level for commercial products, it can be applied in RTS game. So our motivations produce such a priority setup. We care about things which are easy to produce, easy to use, scalable, replaceable. It's more important for us than things like clean code, some performance improvements, or making behavior which is universal for everything. And if we get to the situation that we have some behavior and we want to upgrade it, behavior, which means we want to upgrade it, instead of hiring someone who have time and skill, we generally give it to some as experienced person who made the behavior from the scratch, and that's economical, more economical approach than fixing old stuff. So in the old context, the behavior is working, and we create a new one which works in new context. So this is mindset setup which we use as a motivation source for any behavioral production. Another concept. So because I know the audience here is not AI focused, or not all of you are AI developers, so I want to make it accessible for you, and maybe I want to give you some inspiration sources which can be useful in other fields, not just in AI development. So we again try to be more conceptual, more general. So how we understand our AI system. So there is something. Everything which is black is really black box. So we don't know how it works inside. We just know it is there, it does its job, and we know it somehow communicates with the rest of the world. So we have some simulation, which may be VBS free, which may be Spring Engine, which may be Unreal, which may be even the real world. No, this is not the slide I wanted. So, I mean the real world, the hardware input, and there is some other module which is AI, which again we don't know how it works inside, we just know it receives some events and messages about what's happening in the real world or in simulation. It asks some questions, gets answers, and it performs some actions, sending to the simulation. I take the item, I will shoot to that guy, with some parameters. Good thing on this, we don't need to focus what's here inside, we just focus on what's happening between those systems. It allows us to be more focused and improve this API, which is the interface between those systems. And we are, as I said, no focus time, sorry. Now, end of the concept, and now we get to the practice part. So we are in the second part of the presentation, motivation example on the real customer's input. So imagine this customer for some not named army or military organization, and he wants to make a training where soldiers are attacking some storage, for example. And there is AI guard, which is patrolling around the building, and it has basic behavior which is doing one decision. I am patrolling unless I'm scared. If I'm scared, I run away. That's the goal, what we want to achieve. But yeah, once we get to this, first designers or maybe programmers question is, oh, what do you mean by scared? And usual answer of such customer or maybe player of nota, which is asking some question or some request, some feature, is it depends. In different situations, the fear is defined different way, which gets us to first mock-up of the behavior, some first iteration, and we say, okay, the customer, players doesn't know what they want, so we try to give them something. So there is some simple decision tree. I'm showing the examples on behavior trees, in behavior trees notation, but our talk is not limited just to behavior trees, so but maybe it's too big detail. So it's a decision tree, so I'm soldier, I am patrolling unless there is some explosion. If there is some explosion, I'm scared. Imagine here is some behavior performing scare behavior, here is some behavior which is performing patrolling behavior. And as I said, the customer or player is not sure how the scared is defined, so it can change, and it will change a lot. If you perform iterative development in your team, if you are iteratively delivering something to the customer and get feedback, you figure out very soon that customer is really not good person which knows how the fear is defined, because he just haven't figured out that in given situation he would like to do something. So you give him some production iteration number 3, he will look on that, he will play with it for 2 hours, And then he will tell you, okay, the soldier is scared of explosion, bullets, flames, but if he sees enemy tank, he doesn't react. Why? It's obvious. I would expect that he would do that. Okay, we add tanks, but maybe if the soldier is not experienced and he have, oh, that's the job with the cigarettes, but maybe if he have not friend around him, if he's alone, he will run away, and that's dependent also on his literacy level. So there are bunch of conditions, bunch of rules which can change, and for us, every time we improve such behavior, we have to change this huge pile of conditions, and every time it means changing the whole behavior. So my solution to this, obviously based on the experience, is that I know that the condition changes a lot, so I will outsource it. So I create a different system where the customer can define what the fear hell is, how he wants. And here I will just say, give me the value of the fear. If I am feared, I perform scare behavior. If I'm not feared, I do patrol behavior. And here, the customer can give us 15 times different feedback, and only what we do, we change the definition of fear, but this behavior, based on his first proposition, doesn't change. That's the advantage, because we split the part which changes a lot from the part which doesn't change much. And it has consequences, because if you imagine a huge project, and if you are able to separate just the things which changes a lot, you save the money, save the time of the testers, make it more robust, it doesn't break so much, etc. So, this is just recalibration of the example from previous slide. So to make it run, imagine that I have some solid behavior which is running in parallel to thinking branches. In one thinking branches, I am performing the behavior, so which means I'm scared, I'm patrolling, and on the second branch, I'm simulating the fear. You will see that I already created there some gray boxes. So each box is one behavior tree, and we can consider each box as a separate module. We are, of course, interested in this module because this is our primitive sensor. This is our answering machine, which is answering the question, am I feared? Or am I scared? This is just some notation. It's not important much how those things are connected, but I hope it's understandable that on the right side we do the fear evaluation, and on the left side we do the behavior decision making itself. Stop me if it's not clear, please. Okay, and we are going back to the concept. So again, this graph, and I was showing some implementation. The implementation was in behavior trees notation, but we are not limited to behavioral trees. The thinking about fear can be some function. It can be some FSM, finite state machine. It can be some arbitrary hardware piece. It can be some camera which is just looking at me, and I don't know, maybe it analyzes me. So that's the source of the sensor, and it can be anything. So we are not limited that the sensor has to be some behavior tree, and we are not limited to just one AI creation. This is just architecture, and the important thing is we have those black boxes, and now we will look what's in one of those black boxes. So this is just one example. What came to my mind, you can have your own system. So imagine there is that one sensor. For example, this black box is answering the question, am I scared? And the core module is answering nothing, it's just the control of the body. There are some internal stuff, but you still see there are the gray boxes which identify what's the module, and you will see there is some API which serves us as a communication bridge. And again, the same colors means that orange lines are requests, blue lines are answers, and we see that in this very simple example, the core controlling the body and performing actions is not directly asking the simulation what is happening outside, the sensor does. It communicates with the engine or with the real world, and the core just work with some simplified preprocessed result of the world. So this is another advantage of the system. It somehow simplifies the world around you to be understandable for you or to generally fit to your categories of the world around. Now we get to the definition. There will be 4 rules. We will see that all those 4 rules can be passed or broken, or we don't need to follow them so much, but for the beginning and for constructing some primitive system, those rules are very helpful. So the first, and maybe this rule is one of the basics one and which are important. Sensor is black box which answer one question written in human language. For example, am I scared? And the answer can be just yes or no. You will see that we will benefit from such restriction. If we look inside of the box, the question is answered by evaluating activation function. Activation function will use some API, some system which is using for communicating with the rest of the world. So it can ask the camera, hey camera, what are you seeing? 2 or 1 person or no one or white caravan or something like that, or bird. And also, and this is maybe more interesting, you can ask other sensors about what they see or what's the status of their evaluation. So they can even use the preprocessed data of the world. Third rule, if the sensor is in no state, so previous frame, previous evaluation, it answered no, I do the evaluation again. And if I answered yes, I can run some activation function, I can sleep for some time. It means, in practice, imagine, again we have this I'm scared behavior, and if I'm scared, I know that if I start to be scared, I won't stop to be scared for next 2 minutes. So it doesn't make sense to evaluate fear for next 2 minutes, and I can save some performance. That's one direct benefit from this system. And there are other things you can see there, but they are not as much important right now. And as I said, this B rule, that we can use other sensors' answers, that's the main advantage when we avoid having just one single sensor and we start to construct some systems from single sensors. So we try to build something bigger, which helps us to get performance. We can still say that each module, each sensor is one module. It can have own developer. We can remove it, replace it, because it's pretty straightforward. We know what the sensor is. It answers one question. We don't care what it does inside. We just want the answer. So we can have 2 junior designers. Each of them can design tactical analysis of the battlefield, and we can compare them in the end, and we can just fire the designer who did it first. So that's what we do in the company usually. And yes, and we can use it, we can reuse already created sensors, and we can create straightforward debug UI, which you will see in the example. So just remind what's there, some sensors, some core, and now we get to the complex example. So third part of the presentation, and there start to be, I hope, something more interesting. So keep in mind that this presentation is about AI, but there are no behaviors except that one example at the beginning. We are just talking about sensors. Sensors are evaluating environment around us. They just give you simplified information about what's happening around, and that's the decision-making source for the behavior itself. So we are not showing something as behavior, we are showing just the analysis of the things around us. So imagine that we have simple sensor which is answering simple question. Do I see an enemy? This sensor can be turned on and off. That's equivalent to answer yes or no. And we can create other 4 child sensors are answering different questions, or questions on different level of abstraction. So this sensor is just getting information somehow from the engine, answering this question, and if the sensor is activated, it makes sense to ask him, hey, and I hope all of you know that soldiers are using a clock notation about to say, hey, the enemy is in front of us. They say, enemy on 12 o'clock. We can see it on this example. So there is a group of soldiers going west. For them, 12 o'clock is in front of them. And behind there is 6 o'clock. On the left flank, 9 o'clock. On the top, 3 o'clock, you can see the legendary, which helps us to orient there as well. And here you will see the soldiers. So if the sensors are enabled, we will see next result. So we see on our radar or just by visual sensors that there is someone in front of us. So we enable sensor 12 o'clock. We can use bunch of different approaches how to analyze stuff around us by just choosing this system. You can have 7 sectors. You can have just one sector. You can have just some square heat map or what do you want. I just did this split of the battlefield because for some reason, for my doctrine, for my customer, this is the way how the soldiers think about it, for example. So on the 12 o'clock, I see enemy in this case. In next case, on the left flank, we have guys attacking from the south. You see them? Is it visible for you? Okay. Maybe can we turn the lights off for the images because I think. Yes. Is it better for you? Really? if not, tell me. We can turn the lights back. And something complicated, slightly complicated. If the enemies are attacking from this crazy direction, we will enable both sensors. So enemies are on 9 o'clock and 12 o'clock. Maybe for our AI, this fidelity is good enough. Maybe not, maybe yes, but maybe it's good enough. So we have those basic sensors for recognition from which direction the enemy is coming. We can another bunch of set of sensors. For example, this sensor, based on the data coming from this sensor, can evaluate if there are enemy anti-air units in enemy group, if there are some anti-air robots or airplanes. This sensor is answering the question, is there any anti-ground air? So aircraft equipped with anti-ground missiles. And for example, we analyze ourselves. So we ask, hey, do we have anti-air group in our team? Do we have anti-air support somewhere so we can call someone, hey, help us with some anti-air support? Or we can just have some air transport units which are ready to save us from the battlefield. We will see in next example that this will be enabled, so we know that at the end our group of robots which will be bravely fighting with nasty, crazy AI robots will survive because they have air support, but we will see if it helps or not. And we can expand our system even more. And imagine each of those black boxes, those are separate modules. We can run them in parallel. We can even have each box on different computer if the computation is complex. So this way we can split the performance between different machines and get better performance for the player or server. I could describe each of those sensors and describe the rules, how they are working, but I think for us it's just important there are a bunch of other things. They are in different layers. Those arrows mean that, for example, this sensor is making decision based on data from this and this sensor, and for example, flank sensor based on those 3 ones. I think we should see something in action because, and there's the core. Core is the behavior itself, which does the decisions based on all those sensors data. Yes, so now finally it's the time for the video. If my mouse starts to work, finally. So one day, somewhere in the desert, on peaceful planet, there were robots walking towards the enemy. You see, there are some close fight robots on the sides. There are some rocket robots. There are some artillery robots, and there is also radar vehicle. Those robots are peacefully going through the desert. And we see, as I said at the beginning, they know they have air transport ready to get them if something bad happens. And they are slightly going forward. Now we see there are some nasty enemies coming from that direction. So our group just enabled some of the sensors because they noticed that they see enemy on 3 o'clock and 12 o'clock. It means in the front of me and on the right side. They consider to be flying, so it means for them that the core makes a decision that if enemies are going from this direction and this direction, we rotate our group towards the enemy, and we can see the result. So the closed fighters, the warriors, are getting to the front. Artillery robots are firing from the back. They fix the direction to be still facing the enemies, and also trying to hit that nest robot, which is still not possible to be killed. Oh, no, yeah. And now there is another attack coming from the left. We have seen that the sensors values were changed. So instead of 3 o'clock, now the enemies are at 9 o'clock, and also the sensor which is marking that we were on combat is already activated. So another fight. You see the enemy group is not dangerous, just few guys with shitty weapons. So but there is a big army coming from the north, and that starting problems, so our guys are running away. And there are not just the red bastards coming, but also the aircraft attack, which changes the whole situation also. So we see another bunch of sensors gets activated. So we see anti-ground air shooting at us, missiles, we are dying. We have no AA support, so it is considered to be critical danger, which together with there are more enemies than us, with combat result in it's time to leave. Time to leave together with air evacuation is possible based on this and this gets to another result. It's time to perform air evacuation. The behavior which is using this sensoric system is just 3 decision nodes. It's so simple thanks to this system, and it, based on the information, just call for help. So I hope the help is coming. Oh, yeah, it's coming. And we are saved. So this was our system, and now we get to the conclusions and observations. So you have seen what is one sensor, how we construct systems of sensors, and some other practical observations which we did as part of the development for VBS Free AI or nota AI. So, what our customers and even our business developers or CEO of our company likes the most is that if he sees this diagram, he knows what the AI is thinking about. He knows what is the decision-making process together with behavior trees, and also he can change the naming of stuff. He can change the definition pretty easy for him. He doesn't need to be AI developer. He understands what's happening there, and that's in the commercial AI development very important stuff, because usually it's the hardest thing is not to implement something, but it's hard to implement something which fits someone's needs. So he needs the behavior to perform exactly how he has it in mind, but you don't know what is in his mind. So this way you get to that faster, which saves money. In practice, we made, our experience was that it's slightly easier to get juniors to be part of the development team if they have such a team. It is not entirely whole life saving system, but for sure it speeds up the development even for non-educated AI developers. But the system you have just seen, which may be simple for me or for programmers, which are trained to be crazy guys doing such stuff, but for designers or general testers, it may not be as easy to, maybe they are able to work with the system once it's ready, but maybe they need a lot of time to figure that system out. So the experience is not that we solved the problem entirely, we just saved some time. Anytime you produce something using sensors architecture, you need to document it properly. The graph we were using during the video example is such kind of documentation you need. With such documentation, the people understand what is it about. Without that, it's just a bunch of definitions in which they are lost. So you need some visual documentation, and what's the advantage? If we go one slide back, each of those buttons can be used as a debug features, and if you create a debugger, which is just turning lights on and off, green or red, you have the debugger, and you can visually see what's happening there online once the behavior is running. So this is advantage. You have already the design for the AI debug, some part of AI debug. Second page of observation and conclusions. In the nota project, we experienced that if we try to make such complicated systems, we can anytime, for example, pick the AI dangerous evaluation subsystem, grab it, and use it not just for ground soldiers, but use it also for ships, or use it for builders, engineers. We can use it for defensive building. So this piece of this subsystem, sensoric subsystem, can be just took and reused somewhere. Or if we are not happy, we can just change few items there. Those Lego pieces are what we use in designing variants of behaviors. We don't create everything from the scratch. And maybe that's one thing I forgot at the beginning. Sensors are not just some functions which evaluate the state around you, because they have also the time memory. They know what is now, they can evaluate the function, but they also know what was before, and they somehow have the time context, which in the practical AI development is important thing. And yeah, one bad experience. We delivered and we sold for kind of interesting money product with AI using sensors. The performance of the system was good enough, but I have to say, based on our measurement, 90% of the performance if we just talk about the sensors, were just consumed by the overheads, which were lately optimized. So it very depends on how good you create the architecture, how you implement it, and the first implementation was on scriptless level, so just in Lua, and that was the reason why the implementation was not optimal. But as we see in the next point, optimizations are easy because you optimize all the stuff at the same time, because you have one framework, one approach, one definition of sensor. So if you have evaluator of functions, it's just one optimization which gives the whole system the performance. And yes, the definition of sensor is self-documenting the sensor behavior. So that's another example. And at the end, some numbers. Currently in Nota, we have around 400 RTS groups, which mean brains, which are usually evaluated twice per second, which is for RTS game good enough, controlling around 2,000 units, and size of the group can be 58 robots, and sometimes it can be just one robot if it's some hero or some tech-tier-free killer. And in VBS3, for highly detailed AI simulation, we have around 150 units with 30 FPS. And I don't mean visual FPS for the visualization of the behavior, but I mean the thinking frames. So it's still, I think, good. Yes, there are some concepts and optimizations. I don't think so. I have to jump on that. I would like to maybe use this page for once you have some questions, if you have some. And I would like to thank Martin Groszak sitting here, who created all the videos and art you have seen in the presentation. And now we are at the end, and it's time for the questions. And maybe for the, yeah.
So I would like to ask how many nodes you have in some build that you are using?
You mean 3 nodes?
Yes.
Okay, if we talk about sensors, we have, for example, 15 to 25 types of different sensors, which they are used maybe 10 at the same time for one brain. But if you talk about nodes of behavior trees, we have huge trees which can have hundreds of nodes or thousands of nodes. So not trees you have seen in the example, because this is sensoric trees are pretty small, but the real behavior trees we have in our company, in PISIM, they have hundreds of nodes. And we are just measuring that last time. The whole system controlling military behaviors and civilian behaviors had something around 3,500 nodes. But yeah, but this presentation was not much about behavior trees, so I hope it answered the question. Anyone else?
Do you think this approach is good for a small game, like with the performance, for example, on mobile phones or tablets?
Yeah, thanks for the question, because it reminds me one thing I forgot. Creating such system is not as small that anyone can afford it. So it has some starting cost, but for you, the cost may be much smaller because we were iteratively trying to achieve something. So we did 11 iterations until we get to this state. Maybe it will be faster. And I would suggest such system to game where the AI component is the game mechanic or specific cool stuff. So if you have game where the opponent's thinking is important, if it's the cool game feature, if you have super smart shooter, or if you have cooperative game where AI is able to cooperate with you as a human player, for such thing I would suggest to use something like this. But if you have some silly companion or you just want to chess AI, I think it's not worth to invest time to something like this. But maybe you can be inspired by the general approach, cutting things into small boxes. That's what I would suggest. Because generally, the holy grail of the design is that you find the good size of the piece of program or sub-function or some module, which allows you to focus on that, don't get lost in a huge code base, and that's kind of the robust approach. But also, again, if you hack some game in some jam or in few weeks, get it on Google Play, get as much money as you can, and then you start with some other project, something like this is not good for you, because this is for projects which plan to live for longer than a few months. So I hope, have I answered the question?
Okay, another question. Do you use some more advanced functions like neural networks?
Yeah. This is just a slide which I cut from the basic presentation. My plan was to talk about with you what AI we are talking about and what AI we are not talking about. And I thought it's maybe too out of scope of the discussion, but we can go through that. So it's just the next slide. So machine learning, neural networks, and other statistical magic, that's not what we do. We do rule-based systems which are very good for very well-defined situation, and they do exactly what they are asked for. If you create machine learn anything, image recognition or path planner or something like that, you can get better results than with rule-based models, but you are not able to just dig in there and improve it manually. Generally, if you are army person preparing training, your goal is to prepare a scenario when guys get into the corner, shoot on the convoy, few rounds, doesn't kill anyone, and run away. With some machine learn trained soldier, the soldier will be very good because he always pick different path to the, maybe he will choose a variant path to the target, he will shoot as he thinks is the best, but it's hard for you to control what's happening inside. So this is one type of AI we don't do. We also do more reactive decision makers than planners. And our performance heavy stuff is because we run multiple instances of the same problem, not solving one huge problem. But in the end, we can pick any of those super good AI things, different AI approaches, enslave it and use, for example, machine learning to create one sensor which has machine learning module inside, which is evaluating for us, for example, okay, am I in the urban area or am I in the forest or am I in the open area? It's tactical decision. It's pretty hard to achieve that analysis based on rule-based system, but you can train a model which based on objects you see around identify, am I in the forest, am I in the urban area, or for example, path planning. Path planner can be another advanced stuff which can be hidden in sensor, but maybe path planner is not a good example, but as I say, you can pick one of those advanced statistical models, put them in one sensor as an evaluation function, but on high level, we use just the result, for example, the right path, or do I see solution for this situation or not? On such very high level, very simple decision making level. Because this is AI which is created by people who doesn't care much about math, statistics. They use human understandable terms, and those AI is done by scientists which understand mathematics, which understands statistics, physics, and they are using scientific approaches to improve their models. So they are different type of people, and usually those people on the left, which are including me, are using good work of those guys to use it for our best solution. So that's kind of what is the difference between the approaches and how we use it. What do you like?
I see. I would just think that when it comes to especially the simulations, I do not think that the opponents will be strong enough or good enough. If you want the soldiers to learn something, or you want some commanders, then if you use just rule-based system, it always leads to some patterns which create behavior that is not very realistic and can be exploited.
Yes.
But if you use you can get better
Yeah,
components.
that's the use case. As a game developer, you are maybe interested in robust system which is maybe not always following some exact rules, but in average case is better than some rule-based system. And that's the different case. In our company, we are producing something which is predictable to the most possible extent as possible. So, sorry. So they are not interested in something they cannot control. And in RTS level, in nota, which is game, which is competitive game, so you can exploit enemy, but you just need just very few those learned models to get some tactical analysis, but all other stuff, like the decision making in proper situation, is based on the data coming from the learned. So you have neural network which gives you proper move in given tactical situation, but if you do the move or if you run away home to the base, that's more rule-based system decision. So you can combine those things, and it's based on your use case. So if you are more focused on competitive playing and generally do not care about reproducibility of your scenarios, yeah, sure, that approach is beneficial. But it's nothing against sensors, because, as I said, you can utilize any trained model as a sensor input.
Okay, thank you.
So we have still some time, but yeah. Is there any other question, or I can move the word to the next speaker? Okay. So thank you for the listening.